Assalamualaikum and welcome to my video presentation. First of all, let me introduce myself. My name is Aisha Khan. I'm a student of MS Chemistry Batch 5 and today I am going to give presentation to Dr. Hamad Majid, HOD of Chemistry Department at UMT Sialkot. So the topic of my presentation is BET, that is Branauer Emmett, and DR equation, that is Dubinin Radushkevitch equation. First of all, we have a table of contents here in which we will discuss about the abstract introduction history of BET, what is surface, adsorbents, adsorbate, types of adsorption, factors that affect the adsorption, assumptions of BET, its derivation, its operation, and then we have applications, conclusions, and references. While in DR equation, we will discuss about abstract introduction, development of DR equation, its theoretical basis, Dubinin Radushkevitch equation, applications, conclusion, and references. So, let me start our presentation. The first topic I will explain is BET, that is Branauer Emmett equation. The BET is a vital tool which is used to analyze the surface area, commonly applied in scientific and industrial settings. It also helps to measure the specific surface area of porous materials, offering important details about their structures. This equation builds on the Languir's adsorption model, which focuses on multi-layer adsorption. By studying the gas adsorption on surface, it also used to calculate the surface area by relating the gas amounts to monolayer adsorption capacity. The key components including in equilibrium moisture content, monolayer moisture content, energy constant, and water activity. The BET equation assumes a uniform surface considering the interactions between gas molecule and the material. Its broad application extend to understanding the material properties like dissolution rates, catalytic activity, and the impact of temperature, and the nature of adsorbents and adsorbate on adsorption process. Overall, the BET is indispensable for precise surface area analysis and plays a crucial role in material characterization and gas adsorption studies. Next, we have introduction of BET. The BET is a key tool in physical chemistry used since 1930s to calculate the surface area of various materials. Initially, it was designed for the substances like catalyst, charcoal. It also has evolved to characterize the modern porous materials such as zeolites and metallic organic frameworks, that are MOFs. These materials play a vital role in research and industries like gas storage and drug delivery. Unlike the Languir theories, BET consider multi-layer adsorption, setting the standard for porous material characterization. Recognized by IOPEC, it is the most widely used method for the determination of surface area since 1995. Essentially, it is crucial for assessing the various porous materials. The next we will discuss about the history of BET. In recent years, nanotechnology research has extended beyond the chemistry and into the diverse fields like medicine, energy, aerospace, and information technology. Unlike the bulk materials, where the surface area is less significant as compared to the volume, nanoparticles have size 1 to 100 nanometer exhibit the unique properties. For example, commercial zinc oxide has a surface area 2.5 to 12 millimeter square per gram, while the bulk zinc oxide has a specific surface area that is 54 millimeter square per gram. It's mean the nano zinc oxide has more unique properties as compared to the zinc oxide in bulk. Nano zinc oxide is used in ultraviolet radiation blocking systems, that is sunscreen systems. Surface dominating nanomaterials showcase the pronounced surface level reactions impacting the dissolution, oxidation, and photoexcitation. Precise surface area determination is crucial for predicting the environmental effects and assessing the hazards, essential for understanding the role of nanoparticles in various nanotechnologies. However, the most widely used technique for the determination of surface area is BET, which is named after Stephen Bronner, Paul Emmett, and Edward Teller. In most cases, the BET model also gives information about the moisture content, and the equation for this moisture content is given as this: M naught CAW over 1 minus AW into 1 plus into C minus 1 AW, where the MW represent the equilibrium moisture contents, M naught represent the monolayer moisture content, C is the energy constant, and AW is the water activity. If we plot a graph for the moisture water content, we will get a straight line. This shows that it works very well for the water levels between 0.05 and 0.04. So it's mean it has a limited range. Due to its limited range of water activity, it is commonly used for the determination of surface area of adsorbent. Next, we have a surface. Basically, a surface is a boundary that divides the one substance from its surrounding. In terms of BET, it refers to the solid material surface, especially if the material is porous. In general, the surface refers to both material's internal surface area pores and voids as well as its external surface area. The next is adsorbate. The adsorbate is a material or the molecules that get adhered to the surface of liquid or solid. They get adhered by electrostatic interactions. They may also form hydrogen bonds, van der Waals equations, and other intermolecular interactions. The adsorbate may be liquid, vapors, or solid. The next is, what is adsorbent? Adsorbent has the capacity to attract and hold the molecules of an other substance. In this equation, we can see the dots in green are adsorbate and the black body is adsorbent. The adsorbate get adhered to the surface of adsorbent. Next, the types of adsorption. Basically, there are two types of adsorption, that is physisorption and chemisorption. Physisorption is a physical adsorption in which a physical or weak interactive forces are formed. These forces may be van der Waals forces, dispersion forces, or any other forces. The characteristics which affect the physisorption are weak attractive forces, because in physisorption, weak van der Waals forces such as London dispersion forces and dipole-dipole interactions are formed. Physisorption is usually a reversible process because the forces of attraction are weak, they have low activation energy, and physisorption leads to multilayer adsorption because multilayers of adsorbent molecules can form on the adsorbent surface, with each layer experiencing a weaker force as you move away from the surface. This diagram represents what is physisorption. While in chemisorption, a chemical bond is formed, which is basically a strong forces, unlike physical adsorption, which involves relatively weak forces like van der Waals interactions or hydrogen bonding. This type of adsorption involves the exchange of or sharing of electrons between adsorbate and adsorbent molecule. As a result of chemisorption, higher energy of adsorption as compared to the physisorption. Chemisorption plays a very important role in various chemical and industrial processes. For example, it is helpful in catalysis where the reactant molecules are chemisorbed on catalyst surface. Additionally, chemisorption is also being observed in environmental applications such as removal of pollutant from air or water. However, it is vital for optimizing the catalytic reaction, gas adsorption, and various surface chemistry applications. Next, we have the factors affecting the adsorption. The first factor is nature of adsorbent and adsorbate. The surface characteristics and the affinities of various materials vary from substance to substance. The second is temperature. Adsorption is greatly affected by temperature. This is because Stronger intermolecular forces and enhanced adsorption are generally the result of lower temperatures. The adsorption tends to increase with decreasing the temperature. The third one is pressure. Greater the pressure, greater the adsorbate molecule get adsorbed to the surface of adsorbent. This is because more pressure will enable more molecules to stick to the surface of adsorbent. The fourth one is adsorbent surface area and porosity. More the molecules can be adsorbed by materials with greater surface areas and porous structures. This is particularly important when it comes to solid adsorbents like zeolites and activated carbon. Next, we have the assumptions of BET. The first one is homogeneous surface. BET, like Languir adsorption, is predicted on the idea that material surface is homogeneous and the adsorption happens uniformly throughout without any preferred adsorption sites. Each adsorption site is either vacant or has a single occupant. The next one is limited molecular interactions. In limited molecular interactions, once the adsorbed molecules adsorb, it can act as a single absorption site for the another. No other intermolecular interactions are considered, like including lateral interactions between the adsorbed molecules, the interaction between gas phase molecules. The third one is local equilibrium. The amount of gas adsorbed to the surface of adsorbent is equal to the amount of gas dissolved to the surface of adsorbent. It means adsorption and desorption are occurring side by side. There is equilibrium between these two processes. The fourth one is physisorption. According to this theory, the gas molecule adsorb on solid surface through a process known as physical adsorption, because in this a weak van der Waals forces are formed. The next one is Languir assumptions are easily applicable to each layer. These assumptions include solid surface possess uniform localized sites. Adsorption at one site doesn't affect the adsorption of neighboring sites. The next we have the equation for BET. We derive the equation and then we have the final expression like this, in which P over V into P naught minus P is equal to 1 over VMC plus C minus 1 over VMC into P over P naught, where V is the volume of gas adsorbed, P naught is the saturated vapor pressure, Vm is the volume of monolayer formation, C is the constant, and which is equal to this equation, E minus EL over RT. This is the way how we derive this equation. And the final expression is this. The next is limiting cases that can be distinguished. The first case is when constant C is greater than 1. This means the first layer heat of adsorption is very high as compared to the enthalpy of condensation. And for this condition, P is smaller than P naught. The equation BET changes to Languir equation, and so is the isotherm. The second case is when C is greater than 1. In this case, it's mean the first layer is not completed when multi-layer adsorption has been started. BET equation can be plotted to determine the monolayer adsorbed gas quantity and the BET constant. If we plot a graph, then we will get a straight line equation in which 1 over VMC is intercept, C minus 1 over VMC is slope. This equation represents y-axis and P over P naught is x-axis. Now take the numericals value for slope and intercept to solve Vm and C. We will get the equation like C is equal to 1 plus slope over intercept. From the monolayer adsorption, gas volume, you can determine the total and specific surface area. St is equal to Vm ns over V, where St is the total specific surface area of sample of material. Vm is a monolayer adsorbed gas molecule. N is Avogadro's number. S is the cross-sectional area of adsorbed gas molecule. V is the molar volume of adsorbed gas, where the surface area PET is equal to St over A, where S BET is the specific surface area of a porous material that we have to calculate with the help of BET. The next one is how BET is operated. Adsorption is when gas sticks to a surface, different from absorption, where fluid goes into the solid. Temperature, gas pressure, and how well gas interacts with the solid affect how much gas it sticks to the surface. Nitrogen is most commonly used for the BET surface analysis because it sticks well to the most of the materials and it is available in highly pure form. By cooling the surface with liquid nitrogen, we can measure the amount of gas that sticks to the surface. Then we gradually add known amount of nitrogen gas to the sample. The first step is adsorption. At low temperature, a known adsorbate gas, which we usually use nitrogen because it is available in highly pure form as I already have told, it is added to the solid sample, adsorbed onto the sample surface area at the gas molecules. The next one is formation of monolayer. When the gas pressure rises, the adsorbate molecules arrange themselves in a monolayer on the solid surface. Weak forces cause the molecules to stick to the surface during the first phase of adsorption. The next one is multilayer formation. On the top of monolayer, more layers of gas molecules form, and next we will have the measurement. At each pressure level, the amount of adsorbate gas is determined. This data is then used to calculate the specific surface area of BET equation. This is a simple instrumentation of BET. In first step, there is a degasser which ensures that no other gas present in the chamber, which does not interfere with the process of adsorption. After degassing, we will have evacuate. In this, we have to evacuate the chamber, which make us sure that the chamber is free from any type of impurities. The next one is volume measurement. When the volume measurement is done, basically we use helium. This shows that how much gas adsorbed in the whole process of adsorptions. Once we measured the dead volume, then again there is an evacuator that evacuate all the gases present or all the impurities present. The next one is the main process, that is the process of adsorption. After this adsorption process, one in this container, one is a reference cell and second one is a sample holder. One contains sample and one contains reference cell. In this case, we had to apply nitrogen. Once the adsorption occurred, desorption start. As I already have told, the adsorption and desorption are in equilibrium. The amount of gas adsorbed is equal to the amount of gas desorbed. This is the instrumentation of BET. Nitrogen is introduced into the chamber. This is a helium gas. These are the pressure chambers, and finally this is the data collector which is used to build the isotherms, and this is the sample cell which hold the sample, which is usually the nitrogen in this case. This diagram shows the adsorption and desorption. First of all, the gas is introduced into the chamber which get adhere to the surface. After the formation of monolayer, other layers forms leading to multi-layer adsorption. Then finally, the adsorbed gas get desorbed and again we get a bare surface which is ready for the next process. The next one is distribution of pore size. Basically, there are three types of pore. Micropores, they have width less than 2 nanometer. Mesopores having width between 2 to 50 nanometer. Macropores, they have width greater than 50 nanometers. Next, we have classification of isotherms in BET technique. There are basically 6 types of isotherms obtained. First of all, we have type 1 isotherm. Type 1 is a pseudo-Languir isotherm because it depicts the monolayer adsorption. A type 1 is obtained when P over P naught is smaller than 1 and C is greater than 1 in the BET equation. In this equation, the pores are typically micropores, which means they are once filled with adsorbate, leave no space for the other adsorbent. When the adsorption is limited to few molecular layer as a chemisorption type, and this isotherm is a concave with respect to the P over P naught axis. It means it is concave with x axis. The second is type 2 isotherm. If you compare this isotherm to Languir model, a type 2 isotherm is significantly different. The formation of monolayer is being represented by the broader area in the middle. Here we have the broader area in the middle. When the C is greater than 1 in the BET equation, type 2 isotherm is produced. This is an isotherm that is usually found when we apply the BET method. Monolayer formation is being started at the knee point while the multilayer adsorption has been happened as medium temperature. The third is type 3 isotherm. Type 3 isotherm is obtained when C is smaller than 1 and it shows the formation of multilayer because there is no knee point. It means no monolayer has been formed. It is convex with respect to the P or P naught axis. It is convex. The next is type 4 isotherm. It occurs as a result of capillary condensation. Capillary condensation is basically a phenomena that happens when liquid, typically condensation vapor, is drawn into the pores of porous material by capillary forces. So it's mean in type 4, there is a mechanism of capillary condensation when the pressure inside the solid tiny capillary pores is lower than the gas saturation pressure. This kind of isotherm is produced by BET surface area characterization of mesoporous materials or the materials which have pores in the range of 2 to 50 nanometer. It's mean they are in range of mesopores. The next type is type 5 isotherm. It is observed when there is small interactions between the adsorbate and adsorbent. This type of isotherm is rare, but sometimes it also comes with porous isotherms. The next one is type 6 isotherm. This isotherm, as we can see here, this is the type 6 isotherm. We can see the multilayer adsorption occurs stepwise in a gradually or in a uniform manner if the system and the temperature determine the sharpness of steps that are present in multilayer adsorption. These are gradual formation of monolayer adsorption. The next we have is the formation of hysteresis lobe. Hysteresis lobe is occur when there is a difference between the isotherm for adsorption and desorption. That means even at low temperature and low pressure, there is more gas left on the surface of the material than that was during the corresponding adsorption at same temperature pressure. We have four types. Basically, we have four types of hysteresis lobe. 1, 2, 3, 4. Next, we have the applications of BET. First of all, it is used to determine the surface area. The second one is pore size distribution. In pore size distribution, it is also used to determine the distribution of pores in materials. By combining the BET equation with other models such as BJH or DHM, the Dollimore-Hill method, the distribution of pore size can be calculated. The third is characterization of catalase. It is used to study the specific surface properties of catalase by measuring the adsorption of gas molecules onto the surface of catalase. Information can be obtained about the active sites and the surface structure of catalase. The next one is gas separation. PET isotherm is also used to design and optimize the gas separation process by selecting a material with specific pore size distribution. It is possible to selectively adsorb and separate the gases, which is based on their size and properties. Overall, BET is a powerful tool in the study of porous materials and has a wide range of applications in various fields, including material science, chemistry, and biotechnology. However, it has a few limitations. That is, surface assumed to be homogeneous. Interaction between adsorbed molecules are neglected. heat of adsorption from second layer onwards to be equal to subsequent layers, which is not usually true. BET fails below the temperature 0.05 and above 0.035. The next we have conclusions. In short, the BET equation is a crucial tool in surface science and material analysis. It helps to understand the surface area, adsorption properties, and pore size distribution of solid materials, especially in various applications like catalyst studies and gas separation. However, we need to consider its assumptions and limitations, like assuming the material homogeneity and neglecting the intermolecular interactions when we usually practicing it. Moreover, the BET equation is a useful tool for determination of water activity on solid surface materials, making it valuable in different industries. Overall, it remains a powerful tool that contribute to our understanding of surface science and materials and properties for the researchers and the engineers. The next we have the references. And the next topic is Dubinin Radushkevitch equation, that is DR equation. In modern technology, tiny pores in materials like activated carbons and zeolite play a vital role in absorbing the gases. The Dubinin Radushkevitch equation, used for nearly 50 years, helps to explain how these materials absorb the gases. It is crucial for understanding the processes from material characterization to environmental cleanup. DR equations applications are diverse. It helps in the material characterization, providing the details about the microspore. It helps in gas storage technologies, offering insight into the storage capacity. In catalysis, it also clarifies how reactants interact with the catalyst. Environmental issues like purifying air and water benefit from the understanding of absorbent behavior. DR equation is also used to distinguish between the physisorption, chemisorption, evaluate the surface energy, and models of adsorption. The DR equation theoretical foundation expanded with the Dubinin-Astakov-DA equation, providing a detailed analysis of adsorption process. Considering the heterogeneity factor N, it offers an insight into the material differences. The DR equation is a crucial and versatile tool in understanding the gas adsorption in tiny pores, vital in various applications, that is scientific or industrial applications. The next we have is introduction. In today's technology, we often use the materials like activated carbon, synthetic and natural zeolites, silica gels, which have tiny pores and small holes, which is called micropores. These small openings are crucial for these materials to capture or absorb the substances. Despite the ongoing research by scientists, including Dubinin and his colleagues, there are still important questions that how about these micropores materials absorb the gases and the vapors. However, for almost 5 decades, scientists have used Dubinin Radushkevitch equation to accurately explain how gases and vapors get trapped by these microporous materials. When scientists study how substances stick to the surface at different temperature and create a graph by plotting the natural log of the amount of stuck gas against the square of the sticking force, they usually expect all the points to form a single curve known as characteristics curve. This is a common observation in adsorption research, and the Dubinin-Radushkevitch equation is often used to explain the behavior, especially for the substances below the critical temperature. While the researchers have tried applying these equations to supercritical substances, there are instances where the characteristic curve concept doesn't fit well, and in extreme situations, it may not fully explain the experimental results. Additionally, there are some questions about the BET equation like its pressure range, alignment with Henry's law at low pressure. The precision of calculated heat of adsorption at very high and low pressure is also uncertain. Initially, the DR equation was made to describe the adsorption in microporous materials using the Polanyi potential theory. It can also be explained theoretically, looking at It thorough statistical thermodynamics, a new approach for describing the adsorption in microporous carbonaceous material, especially with various varying pore sizes, consider the material structure and emphasizing the improving adsorption thorough to the molecular potential calculation. This approach provides an ununified understanding of adsorption in pores of different sizes. The next is development of DR equation. The equation was created because the existing theories could not fully explain the adsorption on porous materials like active carbons and zeolites. Dubinin and his colleagues shifted their focus to understanding the physical adsorption on porous substances, leading to Dubinin-Polanyi theory. According to this theory, adsorption in micropores happens by filling the pores rather than forming a layers on a porous wall. The Degard equation is a part of this theory, stemming from earlier Polanyi potential theory developed by the researchers like Goldman and Gregg. An essential parameter of this theory is A, which is defined by A is equal to RT natural log P naught over P, where P is the equilibrium pressure at temperature T, P naught is the saturated vapor pressure, A is the constant. According to the Polanyi, it is the adsorption potential. The theory foundation relies on the assumptions of sequential layer by layer coverage of pore substances. Nevertheless, it was demonstrated that the fundamental idea behind the theory, which concerned the temperature independence of material A, holds true for microporous adsorbent. Then Dubinin and his colleague applied the thermodynamic perspective to Polanyi adsorption potential, describing as a differential molar work of adsorption and representing is at negative free energy, which is represented as del G, and it is given by del G is equal to A, which is equal to RT natural log P naught over P. However, a secondary parameter which is denoted by theta, and this theta is equal to W naught over W. Also, W naught is a total volume of micropore system and W is a volume that has been filled when the pressure is P over P naught. The theta is also equal to F into A by E, or it can also be expressed as F is equal to theta is equal to F into A over E naught B. A is the differential molar work of adsorption. E is the characteristics energy of adsorption. E naught is the energy of adsorption for a reference vapor, like usually it is benzene. And B naught is the similarity constant. On the assumption that the pore size distribution is Gaussian, Dubinin and Radushkevitch arrived at the following expression, which is equal to this expression number 6. The common form of, by combining all the equations, equation number 2, 3 and 6. Equation number 2, 3 and 6. Combining these equations, we will get the final expression of dr equation, which is represented W is equal to W naught exponential into minus P into T over beta log P naught over P whole square. This is a common form of dr equation. The next we have is a theoretical basis of dr equation. The research conducted by Hobson in 1961 demonstrated the applicability of the Dubinin Radushkevitch equation in modeling the gas adsorption, regardless of whether the adsorbents were non-porous, macroporous, or mesoporous. This work inspired the numerous researchers to delve into the both experimental and theoretical investigation aimed to uncover the reasons behind the effectiveness of dr equation. In several instances, these studies have resulted in the expansion or adaptation of the original dr equation. One of the most important extension is Dubinin-Astakov equation, that is dA equation, which have the final expression is this. It is basically a projection or modification of dr equation where n is a factor which is termed as heterogeneity factor. So this is the final expression of dr, a dA equation. The next we have the applications of dr equation in the adsorption of carbon dioxide on the surface of activated carbon. The Dubinin Radushkevitch equation is a tool commonly used to understand how carbon dioxide stick to the activated carbons, helping us to figure out their tiny pore volume and surface area. It comes from broader equation called dA equation, which I already have described how we get its final expression. This is equation derivation, where theta is equal to A over N into N. F into A is equal to 1 minus exponential minus A over E into N. And then we get this final equation. So, the value of N decreases as the activated carbon undergoes burn off, which makes the dR equation suitable for the activated carbons with low to moderate burn-off. However, for those with medium to high burn-off, using the dR equation for carbon dioxide data might give the wrong results. In such cases, the dA equation with N less than 2 is better fit. This can make the apparent surface area from dA higher than 1 from dr, sometimes even more surface area calculated with nitrogen at 77 using the BET equation. Understanding how gas stick to the materials, especially porous ones like activated carbon, is helpful. Different molecules, different temperature, like super cold for nitrogen N2 and a bit warmer for carbon dioxide. Equations like BET for nitrogen and dr for carbon dioxide help us to decode what is happening actually. Doing this for activated carbons from the same start but proceed differently, we might end up with 3 scenarios. The first one is the material structures affect how gases enter the tiny pores. If the nitrogen surface area is smaller than the surface area of carbon dioxide, it suggests that narrow pores are obstacle at entrances, especially at low temperature. This helps to understand the material properties and potential applications. The second one is activated carbon with low to medium microporosity BO behave similarly to nitrogen and carbon dioxide. Both gases can efficiently access and fill the tiny pores, indicating no significant restriction in these carbons. The third one is the way gases enter the small pores influenced by the structure of the material. If the surface area for nitrogen is less than the surface area of carbon dioxide, it implies narrow pores are obstacle, especially at low temperature. This knowledge helps to understand the material properties and potential uses. Activated carbon with low to medium microporosity exhibit the comparable behavior with nitrogen and carbon dioxide. Both gases can effectively enter and occupy the small pores, suggesting that no significant limitation in these carbons. The first way we assume the random formation of small pores with different sizes result a Dubinin-Stokely equation. The second way uses a two-term dR equation but requires dividing the small pores into two classes. The third way involves Dubinin-Astrakov equation. In some cases, using one of these three methods might not be right fit for the specific adsorption data. This leads to the potential inaccuracies in the characterizing the material. So the dR equation read as this, where W is equal to W naught exponent to B into T over beta log P naught over P into whole twice. The equation one is particular case of more generous expression proposed by Dubinin-Astrakov known as dA equation. Equation 2. Equation 2 is linked to the theory that deals with how substance stick to the surface and their energy is spread. In this theory, N tells how wide the energy spread is, and it is connected to how pores are distributed. But it's a bit complicated because the carbon adsorbance and the value of n, which is heterogeneity factor, falls between 1 and 4 when n is greater than 2 for its carbon. Like molecular sieves are those with small and uniform micropores. On the other hand, when n is smaller than 2, it is strongly for activated and uneven carbon numbers. Dubinin and Stockley found a link between n and how varied the tiny pores and when n goes from 1 to 2. When the when the activated carbon has more spaces, the tiny pores become more diverse. If we use the DR equation on these samples, we might get the incorrect result and conclusions. So the goal here is to check if these situations hold true by comparing the apparent surface area, which is obtained with the help of BAT method using nitrogen, because in BAT we have used nitrogen, and in this case we are considering the adsorption of carbon dioxide on the surface of activated carbon. And the apparent surface are obtained with the DA equation using carbon dioxide with the best n values that fits with the experimental carbon dioxide data for different series of activated carbon. So the next is applications of DR equation. The first application is DR is porous material characterization. Researchers frequently use the DR equation to evaluate the porous structure of materials like activated carbon, zeolites, and other absorbents. By fitting the experimental adsorption data to the DR equation, they can determine the key parameters such as micropores volume, surface area, providing the critical insight into the material porosity. The second one is gas storage. The DR equation helps to determine how much gas are adsorbed onto the materials. It also helps in assessing the storage capacity, including the natural gas storage and hydrogen storage for the fuel and the transportation. The third one is catalysis. The DR equations in the domain of heterogeneous catalysis, the interaction between the reactant molecules and the catalytic surface is utmost importance. However, for analyzing the adsorption behavior of reactant molecules on catalyst, the DR equation is very helpful. The fourth one is applications of DR equation to environment. DR equation play a very important role in the context of environmental sciences such as air, water purification. It is also used to remove the pollutants and contaminants from the air and the water. The fifth is distinguishing between physisorption and chemisorption. Like BET, it also used for the distinction of physisorption and chemisorption. The DR equation can be employed by examining the energy of adsorption. It becomes possible to discern whether the adsorption is physical or whether the adsorption is chemical. Surface energetics. The DR equation contributes to the assessment of adsorption energetics by determining the energy of adsorption and the reference energy. This information holds significant value in the realm of materials, sciences, and surface chemistry. The last one is modeling adsorption isotherm. The DR equation is an instrument in modeling the adsorption isotherm, which are the plots illustrating the gas quantity adsorbed by adsorbent. It is concerned with its pressure and its concentration. The utilization of DR equation for modeling these isotherms enhances our understanding and the adsorption process and behavior of these porous materials. And now finally we have conclusion. In summary, the DR equation is useful tool for understanding how gas interact with microporous material. It was initially developed as a semi-empirical model but can also be explained theoretically. Recent advancement has enhanced our understanding, emphasizing the adsorption improvement through molecular potential calculations. When study gas interaction with the materials like activated carbon, we use nitrogen and carbon dioxide. The DR equation is commonly used, but it has limitations, especially for carbons with uneven small pores. Alternatives like Dubinin-Stockley equation may be more suitable for these cases. The DR equation finds applications in various fields from the material characterization to environmental solution and the gas-related technology optimization. Despite of all its utilities, it is important to consider that its assumptions and limitations encouraging ongoing research for the refinement. However, the uncertainties including the valid pressure and accuracy under extreme conditions still does not exist. Further research is needed to address these questions and improve our understanding of adsorption in microporous materials. The last we will have the conclusion and the references. And this is all about PET and DI equation. Jazakallah. Thank you. Allah Hafiz.